To start out today's video, just to review a couple important points when you're going to do discs or washers. First off, you should draw in your example slice perpendicular to the line that you're rotating around. Then the thickness of that slice will tell you if it's dy or dx. If the thickness is in the x direction, or in other words, the width of it is left to right, it's a dx. And if the thickness of it is in a y direction, so going up, down, then it is a dy. When setting up your radius or radii, if it's a washers, it's important to remember that any line that comes from the y-axis is an x, and any line that comes from the x-axis is a y. And that's just based on how our points are defined. When we do coordinates, the distance you move to the right is x, distance you move up is y. So our first example we're going to look at, we're going to use a region that we've seen already in two other examples. We're going to look at that region that is formed by y equals x and y equals x squared. And we've seen that a few times. Now I'm going to erase the other parts just so it doesn't confuse us, because we've seen this region, so we should be comfortable working with it already. This time, however, we're going to rotate it around the line x equals -1. So around that line right there. So you can get a visual of what this is going to look like. Here is that region on the right, rotated around. Notice because our region is not totally against the line that we're rotating around, we need to understand that this is going to be washers. There's going to be a gap in our slices. So we've got to do pi r squared for the outer minus pi r squared for the inner. So our first thing to do is draw in an example slice. Well, your example slice will be in this direction. That is a thickness in the y direction. Therefore, we need to do dy. Because we have points 0, 0, and 1, 1, our y values that we go from, and remember, you always pick for your values of your integral from the original region that you're rotating around something. We have y values from 0 to 1. And we're going to have to do pi times our outer radius squared minus pi times our inner radius squared. I purposely drew those two in different colors. Let's talk about our inner radius to start out. The line that I drew in red plus the line I drew in blue is our inner radius. And the outer radius would be the red, the blue, and the green combined. So from the line you're rotating around all the way to our outside function, the red one is the outer, and the red and the blue combined, that line is to our inner function, our black one there, the y equals x. Now, let's talk about what the lengths of each of these are. The length of the red section is always 1. The reason being, from -1 to 0, that's always 1. No matter where we draw our slice, we could draw it higher or lower, that's always going to be 1. So each of these is going to have a 1 in them. Now, our radii in both cases is bigger than that 1, so we're going to have to add something on. Let's look at the inner radius first. The inner radius, we're adding on the blue section. Well, the blue section is connected to the y-axis. Anything connected to the y-axis is x. So we're going to have 1 plus x. However, since we're dy, we can't put in 1 plus x for our inner radius. We need to know what is x equal to in that case. Well, because that's the line y equals x, x is just equal to y, so we'll have 1 plus y for our inner radius. Now for our outer radius, that's represented when you put all three of those little line segments together, the red, the blue, and the green. We already know the red is 1, and when you combine the blue and the green, that segment, the blue and the green together, is also connected to the x-axis, or to the y-axis. So that's another x. So our blue and green segment together is another x. However, it's a different x. That x goes to our y equals x squared function. We need to get x by itself, so x will equal the square root of y. So this will end up becoming 1 plus the square root of y, which we'll put in as 1 plus y to the 1/2. And that will be our outer radius. And that's the challenging part there, setting up your integral. Now we just need to go ahead and solve. We'll pull our pi out front. We're from 0 to 1. When we FOIL this, we'll get 1 plus 2y to the 1/2 plus y to the first, because square root of y times square root of y is just y. We'll have a minus, and we've got to keep it in parentheses. We'll have 1 plus 2y plus y squared, and this will still be dy. So we'll distribute our negative, and we'll have pi 0 to 1, 1 plus 2y to the 1/2 plus y minus 1 minus 2y minus y squared, and then our dy. And we'll combine our like terms. The 1 and the negative 1 add to 0. We'll have a negative y squared. We've got a negative y, because a plus y and a negative 2y is just a negative y. And then we'll have plus 2y to the 1/2 dy. We'll take our antiderivative, keeping the pi out front. We'll have negative 1/3 y to the third, negative 1/2 y to the second. This y will be to the 3/2. The reciprocal of that is 2/3. 2/3 times 2 is 4/3. And this needs to be evaluated from 0 to 1. So we'll have pi. We'll put in our 1. We'll get negative 1/3 times 1 cubed minus 1/2 times 1 squared plus 4/3 times 1 to the 3/2 minus the whole thing. Each of those, when you put in 0, they do wipe out. So we'll end up with pi times negative 1/3 minus 1/2 plus 4/3. And we've just got to try and bring that all together. 6 would be our common denominator. So we have minus 2 6 minus 3 6 plus 8 6. That'll end up giving us 3 6, which is just 1/2, so we'll get pi over 2. So what that's saying is our volume that we will have of our solid when we rotate it around x equals negative 1 will be pi over 2. All the ones we've looked at so far have had faces of our slices that are circles, so we use pi r squared. In the remainder of the video, we're going to look at 2 different scenarios. We'll look at one that's an equilateral triangle, and we'll look at one that's a square. So let's look at this one. Let's say we had a solid. The base is a circle, and each of the slices, the cross sections, are going to be equilateral triangles of different sizes. So as we slice it, we'll get all different equilateral triangles. Now, note our base is a circle, so we're going to kind of look at this from above. And that's what that middle picture does. The middle picture there puts our circle, it's our base, on a xy axis. Now notice they did tell us that our circle had a radius of 1. That's why we don't have r in this case. We have 1. Now where this y equals is coming from, if the center's at the origin, we know that's really x squared plus y squared equals 1 squared. Well, that's y squared equals 1 minus x squared. And then y is equal to square root of 1 minus x squared. Okay, and that's the top part there. Each of our cross sections or each of our slices is going to have a little bit of thickness, but then the face is going to be an equilateral triangle. So what that means is when we do our integral, we're going to have to do a base times a height. We'll have our dx because our thickness is in the x direction, and we're going to need 1/2 a base times a height. Well, our slices go all the way from -1 to +1 on our x-axis. And here's where the tricky part comes in, to determine what our base and our height is for our area formula of the triangle. And the reason this is tricky is because that's not staying constant. As you get closer towards the middle, the triangles are larger. As you get towards the edges, they're smaller. What this red line here represents, this is the base of the equilateral triangle, and think about it, the point of it sticking out at you off the screen. So it's coming out at us, and the triangle's sitting right on that line. We know this here should be y, because it's connected to the x-axis. That's where this y comes in. Because this is the same length, that's just another y. Now, we know an equilateral triangle has all 60-degree angles, so these two are each 60, and we know each of these are 30 when we drop an altitude. Well, normally a cross of 30 is 1. We have 1y. So that means everything was multiplied by y. So normally a cross from 60 square root of 3, so we have square root of 3y. We're not going to end up needing it, but like side BC, the ones in the equilateral triangles, 2y. And we already kind of knew that because we had y plus y on the base. So our area of our triangle is going to be 1/2 our base, which is 2y, times our height, which is square root of 3y. Well, 1/2 times 2, that is 1. 1 times square root of 3 is square root of 3, and we'll have y squared. Now keep in mind, we don't have pi r squared here. Our face is not a circle. Our face is a triangle. So this is what we want. This is our area of our triangle, square root of 3 times y squared. But we can't put that in for our area because we have dx. We've got to replace y with what we know it is equal to. And we know that y is equal to square root of 1 minus x squared. So we'll really have square root of 3 times square root of 1 minus x squared squared. Well, your square and your square root cancel out, so we just have square root of 3 times 1 minus x squared. And that is what our area will be in terms of x, so we'll plug that in here. Oops, this is a 3, not an x, sorry. So now that we have that set up, we're just going to take the integral. The square root of 3 is constant, so just like we do when we have a pi, we can throw that out front. And we'll take the antiderivative. The antiderivative of 1 is just x. Oops, that should be a square root of 3 again. So we'll have x minus 1/3 x cubed is our antiderivative of x squared. And we've got to evaluate this from -1 to 1. So we will have square root of 3. Then we'll have 1 minus 1/3 times 1 cubed minus the whole quantity, -1 minus 1/3 times -1 cubed. So that's square root of 3. We'll have 1 minus 1/3. Here this will be a -1. We'll have a -1 times a -1/3, so it'll be a positive 1/3, and then we've got to distribute the negative. Minus a -1 will give us a positive 1, minus 1/3 will give us a negative 1/3. Keep in mind these ones are like saying 3/3. So 3/3 and 3/3 is 6/3. Minus 2/3 will give us 4/3. So we really have square root of 3 times 4/3. Or in other words, we have 4 square root of 3 over 3. Now what that represents is that is our volume of our solid. That original picture we had that had a circle radius 1 and had triangle, equilateral triangle cross sections has a volume of 4 square root of 3 over 3. So notice the difference here is we weren't doing pi r squared. We were doing 1/2 base times height. We still had to decide our thickness of our slices is which direction, decide dy dx. We still had to, after we found our area, make sure it's in terms of what we had, in this case x, so we had to sub in our equation. So we'll look at one more example. This time we're going to have the volume of a pyramid that we're going to find whose base is a square with side L. Now notice L, we don't have the value of it, but it's a constant. It's always staying L. And whose height is h. Again, we don't know the value of h, but it's a constant. So L and h are numbers. They're not variables. To help us find this, we're going to tip our pyramid on its side. And we're going to put the vertex of the pyramid at the origin. What this allows now is when we do our slices perpendicular to the x-axis, we have squares. Therefore, we won't have pi r squared because our faces of our slices are not circles. We won't have 1/2 base times height because the faces of our slices are not triangles. Here we'll have side times side because it's a square. Now, let's call the side of our square S. In this picture, this is a side view of our pyramid. We know the base of the pyramid we are calling L. The whole thing we are calling H. We're going to call a side of the square S, and we know any distance from the y-axis is just x. Well, by assigning those different letters, we can set up similar triangles. Those triangles are similar by angle, angle. So we know x relates to h as s relates to L. Well, when we cross multiply, we get xl equals hs. And when we divide by h, we get that s is equal to xl over h. Now, keep in mind, what is xl over h? L and h are constants. X is a variable. The thickness of our slice here is in the x direction. So that's why it's valuable to know this. We knew that our area was side squared, but we can't put s in because we're going to be a dx because our thickness is in the x direction. Now, our x values in this pyramid, we're starting at 0, and the last one ends at whatever h is. So we'll be from 0 to h. And we want to do side squared, but we can't put s in there. So we've got to take what we know our side is and square it. That means we'll get x squared, L squared over h squared. And that is our area function of our face. And now we have set up our integral. We just need to evaluate it. Now keep in mind, L and h are constants. They are not variables. We know we can pull constants out front. And now this antiderivative is pretty straightforward. We'll keep the L squared and h squared out front. We'll have 1/3 x cubed, and we're going to evaluate from 0 to h. So we'll have L squared over h squared. times 1/3 h cubed minus 1/3 times 0 cubed. That wipes out, so we just have L squared over h squared times 1/3 h cubed. When we multiply that together, we'll get L squared h cubed over 3h squared. Well, two of the h's will divide out, leaving us with L squared h over 3. And that is our volume of that pyramid because, again, remember, L and H are values. Specific values in our pyramid, they are not variables. That's all for today's video. We'll see you next class, period.